So, one of the downsides of improvising as I stand on the board is that I occasionally forget something. So last lecture, Yun told me that I forgot to show why we optimize the measure that EM optimizes. And that reminded me that I didn't cover Jensen's inequality. Had I shown it, I would have needed to use Jensen's inequality, and then it would have reminded me to cover Jensen's inequality. So I didn't cover Jensen's inequality and I didn't show it, so I'd like to do that now. So I'll start with Jensen's inequality, because it's a very useful thing to know and have. So I always get confused between convex and concave, so I'll use the definition. By the way, I highly recommend the Adam Berger's tutorial about EM algorithm, which is linked to from our website. So I'm going to follow his presentation. Let me do it with a log function, something that looks like a log function. So the function that looks like this is called concave. This is f. So this is some dimension x, and this is f of x, and this looks concave. And in one dimension, there's a very simple condition for concavity, and that is that the second derivative is strictly negative. And conversely, we could say that the function is convex if its second derivative is strictly positive. That means the function goes like this. Now, in higher dimensions, it may be harder to determine whether a function is concave or not. It has to do with the matrix of partial derivatives, the Jacobian, and whether it's that matrix is definite positive. Also, the definition of concavity and convexity exists even for functions that are not necessarily differentiable. So this definition talks about the second derivative, implied that the function is twice differentiable. But you can generalize convexity and concavity to functions that are not differentiable. For example, you can say that this function is concave in some sense, even though it might have some big jumps. So I'm going to show you a property of convex functions, but we can use that property as a definition of convex functions as well, or concave functions, same thing. So the property I'm going to show you is what happens when you connect 2 points here with a straight line. So if every point along this line is lower than the arc, so if the chord is always lower than the arc, for any 2 points that you connect on the arc, we say the function is concave. So that could be thought of as the definition. For differentiable functions, you can say that this is the definition and that this is a property. Either way. So we'll call this point A. Lowercase a is good enough. We'll call this point B. And this, of course, is f of A. And this is f of B. And I will take some point along this line, let's say this point. It's somewhere between A and B. We will express it as a linear combination of A and B. So maybe it's C, and it's equal to lambda A plus 1 minus lambda B. So as we vary lambda between 0 and 1, we move that point from A to B. Okay? That's this point. And then this point is f of lambda A plus 1 minus lambda B. That's this point. I'm sorry, wrong. It's this point. What is this point? This point is a linear interpolation. I'll put it here. This point is the linear interpolation of these 2 points, right? Of this and this point with the same coefficient. So it's lambda times f of a plus 1 minus lambda times f of b. So look at the difference. This is a linear interpolation of the function values. This is the function value of the linearly interpolated point. So what do you do first? Do you apply the function first, or do you apply the linear interpolation first? That's what tells them apart. And they're not the same. And clearly, by the definition of concavity, this point is higher. So I will put, this sign between them. Greater than equal if lambda is 0 or 1. But if lambda is not 0 and not 1, and it's a strictly concave function, there will be a strict inequality. So what I showed here is that for concave functions, the linear interpolation of the function values is less than or equal the function of the linear interpolation of the values. For a convex function, it's going to be the other way around. We're going to invert this thing. This is true for any a and b, and for any lambda. It is not difficult to generalize it to not just 2 points, but 3 points, or 4 points, or any number of points. So if you have points a, b, c, d, e, you can think of a linear interpolation of the points, sigma lambda I. So let's say the points are x1 through xn, and you can combine them with some weights, lambda I xi, where the sum of the lambda i's is 1, right? And each lambda I is between 0 and 1. So this is generalization to the n cases. I can take the linear combination of the xi's and feed it into the function, or I can linearly combine with the same wi's the function value of the xi's. Here I'm linearly combining the function value. Here I'm linearly combining the x's and then applying the function. And if f is concave, for f concave, I know the answer is going to be, the relationship is going to be like this. And again, except for the extreme cases, this inequality is going to be strict. If the function is strictly concave, except for the extreme cases where all the lambdas are 0 except one lambda is 1, it's going to be a strict inequality. This is true for any finite number of data points x1 through xn. It is actually also true for an infinite number of data points, and it's even true for the continuum of points. So if I converted this into an integral, f applied to the integral over the integral with this integrand is going to be greater than or equal the integral of f. I can write that down. It would be integral of some function gamma of x. This time its index is going to be x rather than I because it's not discrete. F of x dx is going to be less than or equal f applied to the integral, the integral of delta x dx. Under the condition that this lambda function Remember the condition we had that it was between 0 and 1 and it sums to 1? Well, here the condition is simply going to be that lambda of x dx sums to 1. What did I miss here?
X.
X, thank you. Delta x times x dx. The integral here sums to 1, and delta x itself is greater than 0, greater or equal 0 for every x. By the way, this condition might hold even if this is negative. I'm not sure. Maybe it doesn't. But it certainly holds under these conditions. So you can think of the lambda as a probability distribution. Right? It's whether the discrete case or the continuous case, the lambda can be thought of as a probability distribution where if lambda I are probabilities of event I and they sum to 1, or lambda here is a PDF as a function. So if you think about it as a probability distribution, either in this context or in this context, this integration, which integration should I start with? This integration can be thought of as an expectation. The expectation of x under this probability distribution. So I can write it as expectation of x under some distribution lambda, which can be thought of as some probability. So let me use P, some probability distribution. And then I apply F to it. And here I take the expectation under this distribution P of F of x. And this is less than or equal for F concave. This is Jensen's inequality. Jensen's inequality says that for a concave function f, you can relate, and for any distribution p, what we called lambda before. So that's the beauty of it. It doesn't matter what distribution p. For any distribution p, it could be discrete distribution or continuous distribution. The expectation under the distribution of f of x can be related to the f of the expectation of x through this direction of inequality. What would it be for negative f? Well, if f is concave, negative f is convex, and vice versa. So you could rewrite the Jensen inequality for a convex f, and the direction of the symbol would be inverted, or you can just multiply both sides by -1 and invert the symbol. So this is the general Jensen inequality, and then Jensen inequality is often applied to one particular concave function, the log function. But it also applied to many other functions. Log of x is concave. Log of x looks like this. Not exactly. It looks like this. Right? It hits here at 1. Log of 1 is 0. Log of values between 0 and 1 go quickly to -infinity. And of values greater than 1 go to infinity, but in a diminishing rate. This doesn't asymptote. It keeps going up, but it goes up at a lower and lower rate. So you can see that it kind of looks concave. You connect any 2 points, and any point along the way is lower than its point above it. Lower than the chord is strictly lower than the curve. So this is Jensen inequality, and now you have to cut and store it in your drawer and keep it aside, and I will go back to the EM and see where it's used. So in EM, we are still using the maximum likelihood principle. We're still trying to maximize the likelihood of our data. So we're trying to find the value of the parameters that give the data the highest possible likelihood. Our problem is that we have some hidden events. And I really like the notation we used in the previous lecture that I think Yoon has suggested, is that we have x1 through xn. In general, there's an xi. And then there are events, hidden events, hidden events. They could be h1 through hn, but that within each one, there may be multiple latent variables that we define, that we called hidden event hi is captured by binary random variables, RVs, and we call them zi, comma j. So the I is the same I from H, but the j could be an index over multiple things. For example, if you have a mixture of Gaussians, xi would be point number I, h sub I would be which of the 20 Gaussians generated it, and there will be 20 zi's. So it'll be zi1, zi2, zi3, zi comma 4, zi comma 5, all the way to zi comma 20. One of them will be 1, and the rest will be 0. So that's my notation. And now I want to write down the likelihood, the log likelihood of my data, x1 through xn, conditioned on my parameters. So in general, the xi's may not be independent of each other, but in the case of the mixture of Gaussians, they are independent of each other. So I could write this as log of a product of the likelihood of xi given the parameters. And this becomes, log of the product becomes the sum of the log of the likelihood of xi given parameters. What I do next is I have to realize that I don't have an expression for, or I have an expression for how to generate this, but it depends on the hidden events. So I'll write this down as sum, this is sum over I of log of, and now I'm going to sum here over P of xi hij for all possible values of j.
Hi equals j.
I'm sorry?
You mean hi equals j?
I don't mean hi equals j.
So we haven't defined hij.
Oh, I'm sorry. Yeah. So I can write, so now I have to choose between z or,
You mean zij equals 1.
yeah. Yeah, but that assumes I can always take the z's out. So let's see, how did I decide to write it here? Let me just write hi. But then it's not a sum. I want to sum it. So which one should I write? That's where I always have my problem.
You can write HI equals J. That's an event.
Okay. H equals Z. That's good. That's very good. And then I know I want to sum over my J possible events. Okay, so I'm just looking at this part for one particular data point. And that particular data point, I use the law of total probability that says that P of x equals sum of P of x comma y summed over y. Okay, this is a marginalization of this.
Now remind me what is that Zij?
So Zij I may not even use here. I just Zij is a random variable that captures in a binary way what the hidden variable is. So I can represent a hidden event in one of two ways. I can represent it as an h, which is a variable that has one of, say, 20 values. And hi would be the number of the component of a Gaussian used to generate point xi. Or I can represent the exact same information with 20 z variables, each one of them being either 0 or 1, and further requiring that for any I, one of them be 1 and the others be 0. It's just a different way of representing, formulating my hidden events. The reason Zij's are useful is in the usual case of a likelihood function that comes from an exponential family. It turns out the likelihood is linear in the Zij's, and therefore we can substitute the expectation of the Zij's. Okay?
What does J mean?
Okay, J is an index both here and here. It's an index over all possible hidden events that could have happened. We can ignore Z. I think we can do all of this with H for now. Okay? So H is captures the hidden events that we have not seen, and J is an index over all possible hidden events that could have happened. And here I'm summing over. My goal is to know the probability of xi, but I do it by using this thing to represent it as a joint probability over xi and some hidden event summed over J. Now, I will copy this. I will start with this. I'm breaking it down into two parts. So the theta is present everywhere, but I broke down the joint probability of x and h to the probability of h times the probability of x given h. I hope I did it in the right order. You tell me. I think I did.
So are you trying to derive the auxiliary function?
No, I'm not trying to derive the auxiliary function. I'm trying to use Jensen's inequality, because the auxiliary function has different definitions by different author. Which one is the auxiliary function? It could be either the...
The way I did last week was different from this.
Okay. All right. If I get stuck, I'll change it, but I don't think I'll... okay. Yeah. Okay. Okay, so now all right, let me try and see if it makes sense. The alternative would be P of x plus P of h conditional x. And I want to do it specifically for one given x. P of h would be the expectation. So that might be, yeah, okay, I think it's the other way around. I just have to break it down in the opposite direction. So P of xi, and here it's, yeah, P of hi equals j given P of xi. So I still use the chain rule, let's just use it in the opposite direction. I broke it into P of xi times P of hi equals j equals xi. Okay? And now is the moment I was waiting for. I recognize this as a probability distribution for any xi. It's some fixed probability distribution. By the way, the interpretation is that you're getting some point in the mixture of Gaussian somewhere out in left field, and that implies for you, given the current value of the parameters, the posterior of the hi, which mixture it came from. So this is kind of the posterior, what we call the posterior for point xi. Different points xi would have different posteriors, but the important thing is this is a probability distribution, and therefore it can be used in Jensen's inequality. I have a log. I have something that I'm summing weighted by some probability distribution. So I can write it as sum of I log of expectation of this something, P of xi given theta, expectation under this distribution, which is hi distributed, distributed hi distributed conditioned on the x, distributed conditioned on x being I and theta. This is what I wanted to get to. I start from the likelihood of the data, and I ended up with a sum of the log of the expectation under some distribution of the probability of a particular data point. And now I use Jensen's inequality to bound it with an inequality. So this would make it, what would it make it? I have to remember to do this in the right direction. Log E of log is greater, so log of E is smaller. So this would make it less than or equal. No? Here, I'm going to invert these. So since log is concave, E of log of something is less than or equal log of E of something, right? And here I have log of E. So this is going to be greater than? You tell me. I get confused. Greater than? Okay. Greater than. So I'm actually applying Jensen's inequality separately for every value of I. You realize that this summation does not participate in my Jensen argument. It's true for any particular value of xi, so it's true for all of them together. Sum of I, expected value of the log, expected value of the log of P of x of I given the parameters. So what I found is this is a lower bound on the likelihood that I was looking for. And in Adam's tutorial, he has a nice picture. So this is less now. I gave you a picture last time of the auxiliary function and tried to argue hand wave. I think his argument is more accurate, but I'm still looking for the picture. Maybe he doesn't have the picture here. Maybe it's... I'll create my own picture. Here's the likelihood function that we're after as a function of the parameters. So I'm showing it as one dimension, but you think about it, it's really many, many dimensions. We are interested in the highest point. We're starting from some point. What we found is an alternative expression that is guaranteed to be smaller than the likelihood. So it bounds the likelihood from below. And it's going to be convex so that we can find its maximum. And we find its maximum, and then we go to the actual likelihood function and put another one there, and so forth. So it all comes out of the Jensen's inequality, specifically applied to log. Now, Yunus mentioned the auxiliary function. You can think of the auxiliary, there are two alternative ways of defining the auxiliary function. It could be this function itself, or it could be the difference in the likelihood between this function and the true likelihood. So if you talk about a difference between them, you can prove that it's always positive and it agrees on the point you're at. So the Adams inequality, Adams tutorial explains this in great detail, and Yoon created a nice derivation which he's going to put online.
Yeah. But for this one, I'm not sure if this completes the chain.
Okay.
Yeah. Let's talk after class.
Okay, sure.
Yeah.
Quick question. Does it matter that we don't know the distribution under E? The H given X.
So we do know the distribution under E for the tentative values of our parameters. Right? So look at this here. We do know, if you remember, we called it the posterior. We said that if we assume that these parameters tentatively, then we're given a certain data point, we can deduce from that how likely is this data point to have come from each one of the components of the Gaussian, from each one of the Gaussian components. Right? To remind you, it was e to the negative xi minus mu j squared over 2 sigma squared divided by sum of e to the negative xi minus mu j prime squared over 2 sigma squared j prime is summed over. It was that's the first thing we did when we first did the iterative procedure for mixture of Gaussians without justifying it, without calling it EM. I just said, let's calculate. Suppose we assume that the lambdas are equal and the mu's are whatever they are here. Given a data point, how likely is it to come from A or from B? Remember that? So this is what this is. Okay, we're a little bit behind, so let me move ahead to HMMs. Oh, I can leave this. HMMs are an example of a latent variable model that is more complicated than the mixture of Gaussians, but still falls very nicely into the general family of the exponential family of likelihoods, and therefore has a very nice EM solution, which is used all over the place. It's used in speech, and it's used in language, and it's used in vision. It's a very, very powerful method. Let's go to our favorite sentence. Mary saw Jane standing, or maybe I'll do the time flies like an arrow. It's much more polysemous. So time flies like an arrow. To those of you who have not seen this sentence before, it's a very famous sentence because it has many, many legal parses. English. How many of you have not seen this before? Good. So the thing I'm going to focus on is the parts of speech. So what part of speech can time have? I guess just one, maybe? Two? Oh yeah, this could be the imperative. Time flies. You know, please time them. Okay. So there's a noun here, and there is imperative verb.
You don't have to write imperfect because that follows from the rule, from the grammar rules.
You mean of the parse? It's the only one that would be.
Yeah.
Yeah, but I'm not doing it that way. Oh,
Part of speech here, it can just be any word.
I guess it could be any part of speech, but I still like to say that there are many of them. So there's a regular noun, and there's a verb imperative, and there's a verb just what VBS, like
So
first person, second person,
it's just VB.
VB, E,
Yeah, no, VB.
VB.
Yeah,
Okay.
simple VB.
Okay, it doesn't matter. The point is there are multiple parts of speech. Flies, there's a plural noun, like the things you're trying to kill. And of course, it's a verb. I think it's VBS, right?
It's written
VBZ? Okay, I'm sorry. Talking to language technologists is dangerous. Any other part of speech that comes to mind? Okay, like is a verb. And these days in the Facebook era, it's also a noun. Right? It's also an interjective, right? In teenage girls' conversation, like they say like all the time, right? And what else is it?
It's a preposition.
It's a preposition. N is a determiner. And arrow, it's just a noun, singular noun. Okay. The point is, there are multiple, and if I start from trying to list all of them and then trying to connect them, there are many combinations of them. So I'm not going to try to fully parse. I'm not going to try to create a full syntax tree of everything. I'm working at a lower level, but higher level than just an n-gram of words. So the model I'll be using would be a latent variable model, which is a part of speech-based bigram, let's say. So a part of speech bigram model. It looks like this. I generate part of speech 1. I generate part of speech 2. I generate part of speech 3. I don't mean these indices are token indices, not type indices. So I'll just go, okay, fine. I generate part of speech 4. I generate part of speech 5. And these parts of speech are generated using bigram dynamics. So this part of speech, well, let's start with a unigram. As part of speech unigram model says that every part of speech is generated independently, and it then gives rise to a word. Word 1, word 2, word 3, word 4, word 5. If I did that, the model would be very similar to the mixture of Gaussian model, except instead of being a mixture of Gaussian, it's a mixture of multinomials. Because I choose which part of speech with lambda, probability lambda, one of the parts of speech, and then given that lambda, instead of drawing a number from a Gaussian, I draw a word from a multinomial. And the likelihood of something like this would be likelihood of word 1 through word n would be a product of the likelihood of each word, and the likelihood of each word would be a sum over the lambda associated with each part of speech. Now I'm summing over part of speech types times the probability of a word given that part of speech. This is the multinomial equivalent of a Gaussian. Every word is drawn independently of every previous word by a two-step process. The first step is hidden. I choose the part of speech, but I don't tell you what it is, and then I draw a distribution from that part of speech. Because the part of speech overlap, namely the same word could be generated by more than one part of speech, when you see a word, you don't know if it came from this part of speech or from that part of speech. But you can still run the same kind of EM algorithm to estimate maximum likelihood parameters here, both the lambdas and the multinomial associated with each part of speech. I should tell you that actually it's a little problematic because there are multiple values of the lambdas and of the multinomials that will result in the same likelihood function. So statisticians call that a non-identifiable model. Non-identifiable means you cannot identify the value of the parameters fully, even if you have as much data as you want, because whatever data you have and as much of it as you have will give the same likelihood value to multiple different combinations of parameters. So in a sense, it's a redundant model. It uses more parameters than are really necessary. But that's just a side note. That's not what we really want. What we really want is not a part of speech unigram. What we really want is a part of speech bigram. We want to somehow benefit from knowing that which part of speech was chosen here affects which part of speech is chosen here. For example, if this is a determiner, like a, the, or n, then this is likely to be either a noun or an adjective. It is not likely to be a verb. Right? So there are strong constraints, strong bigram constraints, that operate between adjacent parts of speech. So what we really want is to put arrows here and convert this into a bigram model. This is still hidden, but now I want to take into account not only what part of speech gives rise to what word with what probability, but also how one part of speech affects the probability of the next part of speech. And now I need to change, this is the unigram model. Now I need to write a bigram model, bigram likelihood. And the likelihood here is going to be a little more complicated. It's going to be the likelihood of word 1 through word n is the product, I, of likelihood of a particular word, likelihood of a particular combination. Okay, so let me write it in big. What is observable here? Observed is W1 through Wn. What is latent, unobserved, hidden, is the underlying parts of speech of the sequence, right? Now what should I call it? In the slides, they don't call these words, they call these O for observable. And what do they call the hidden part? States. Okay, so S. S, part of speech, has S in it. That's good enough. So we'll call it S1 through S. Yeah, small n. That's good. A hallmark of where latent models are and where EM comes to the rescue is that it's easy to write the likelihood function assuming that you know the hidden, like relying on the hidden events, but it's hard to write it not relying on the hidden events. So I'm going to write here the probability, the joint probability, or the probability of, or the complete data, it's called the complete data probability, complete data likelihood. The complete data likelihood is going to be, shall I write W here, or shall I write O for observable? When we switch to the slides, they're going to use O for observable. But I want you to think in terms of words and part of speech. What do you want? O or W? W. Okay. I'll call this entire sequence big W, and this entire sequence big S. Okay? So I'm going to write the joint probability of big W and big S, of both of these sequences together. That's easy to write because I can tell you the generative story of how they were generated. In fact, you know how they were generated. First, we generated the first part of speech. So P of S1 given beginning of sentence symbol. Then, knowing what the part of speech, the first part of speech was, we generated a word from it. So we generated we generated word 1, condition on knowing S1. So we generated this. I can do it the other way around. I could go through and generate all of these, and then come back and generate these from them. Or I can say, it doesn't matter what order we do it. Or I can say, let's generate this, then let's generate this from it, then let's generate this from this, then let's generate this from this. I'll do the second way, but it doesn't matter how you write it. It's the same thing. So I generated the first. Now I generated the word from this. Now I'm going to generate the second part of speech from the first part of speech. So this is S2 given S1. That's this link. Then the probability of word 2 given S2. It's this link, etc., all the way to the end. Probability of Sn, condition on Sn minus 1, times probability of Wn, condition of on Sn. I created a very long chain of 2n multiplications. 2n factors multiplied together, n of them for accounting for the part of speech sequence, and n of them for accounting for the word sequences that come from them. So I can write it in the more general form as a product. I goes from 1 to n of P of Si given Si minus 1, where I understand Si minus 1, if I is 1, S of 0 is the start of sentence condition, times P of Wi given Si. So it is easy to write the complete data log likelihood, or likelihood in this case. Now, I observe that there's a finite number of parts of speech, maybe 10, maybe 20, maybe 30. And that any part of speech could, in principle, follow any other part of speech. You may decide that after a proposition, you cannot put another proposition. Or there may be some specific connections that you say, no, that doesn't happen. I would urge you to be careful, because you never know. Somebody can always stutter and repeat something, right? But in the general case, let's say that every part of speech can follow every other part of speech. That would be an example of a Markov chain, a fully connected Markov chain. So what is a Markov chain? I think we already know what a Markov chain is, right? A Markov chain is when you have a bunch of states, say S0 through S sub big N, and you transition among them, and what the transition probability depends on determines the order of the Markov chain. So a zero-order Markov chain means it does not depend on anything. A first-order Markov chain means that it depends only on the last state you were in. A second-order Markov chain means that it depends on the last state you were in and the one before that, and so forth. So word bigams and word trigams and word unigams are an example of Markov chain, right? We talked about that. What kind of Markov chain is underlying this process? First-order Markov chain. It depends on where you are, but on nothing else. So a first order means that the probability of Si being something, some particular value, no, it's not S. Use Q. The random variables are Q's, not S's. The S's are the values they take. It's easy for me to fix them for you. You know, HMMs have so much notation that I find that notation is the most confusing and difficult part, and that the underlying idea is actually much simpler than it appears. I apologize for that. Put Q's everywhere. Q, Q. Really? Well, in the slides that we've been using at CMU for the last 25 years, it's always been like that. So let's make here a clear distinction. S is the set of all possible part of speech. So noun, plural noun, verb, verb this type, adjective, all of that. There's maybe 20 or 30 of them. Qi is a random variable with or designating the part of speech of word I, or Wi. So the S set is a set of types. The Q's are tokens. So Q7 could be verb. Q8 could be, interjection. Or we may not know what it is. So Q's are random variables. S's are not random variables. They're constants. There's S1 through S50 for the 50 different parts of speech that there are. Okay, so now I'm in a position to define what a first order Markov chain is. A first order Markov chain is one that says that the probability that Q sub I equals some S sub J conditioned on some S, conditioned on Q sub I minus 1 equals something, and Q sub I minus 2 equals something, and Q sub I minus 3 equals something, etc., is the same as the probability of Q I equals some S given Q I minus 1 equals the same something. In other words, whenever you see this long dependence, you can chop it off right here. It only depends on the previous state and nothing else. That's the definition of a first order Markov chain. And we can draw a beautiful picture of S0, S1, S2, S3, all the way through Sn. These are the fixed set of parts of speech that are possible, and we can draw arrows between them for the transitions. So the arrows go every which way. In fact, they go backwards too. Every node is connected to all other nodes. I went here, went there. Let me draw a simple one. S0, S1, S2. 1, 2, 1, 2, 1, 2. But in the general case, if you have n or n plus 1 possible parts of speech, every part of speech can be followed by every other part of speech, and the arrows may represent the probabilities that this one follows this one. So these probabilities, since they only depend, all right, one more change. Let me call the running index t for time. I'm sorry. So this is t minus 1. I'm trying to converge towards the terminology used in the slides. T, qt, and qt minus 1. So now I'm good. I want to go from I to j. So I want to say that the probability that at time t, or at word t, the part of speech was sj, conditioned on the fact that at the previous time step it was si, and at the time step before that it was s something else, and the time step before that it was s something else. Really, it doesn't depend on those something else's. It only depends on this is j, and this is si. So the only thing I need to capture is the probability that given that at time t minus 1 I was in state I, what is the probability that at time t I'll be in state j? So this captures the transition from state Si to state Sj. I will call these the transition probabilities. And I will capture them with the simple Aij. Aij is the probability of transitioning from Si to Sj. And since Aij has two indices, they can be represented by a matrix that goes from 0 to big N here, and from 0 to big N here. For some strange reason, I start counting my possible states with 0, not with 1. So there are n plus 1 rows and n plus 1 columns, and the entire matrix I will call big A. Sometimes I'll put double bars here to remind you it's a matrix. And it consists of elements like Aij. The matrix does not have to be symmetric. Aij does not have to be equal to Aji. And there's nothing special about the diagonal. You know, Aii is a value like any other value. You can have a noun and then go back to another noun, or an adjective and go to another adjective. Every column here, every row here represents a probability distribution. So every Aij is a number between 0 and 1, because it's a probability. And summing Aij over all j's should give me 1 for any I. Because if I stand here, and I can go either to here, so I forgot to put the self loops. And there are self loops here as well. Go from S1 to itself, go from S2 to itself, go from S0 to itself. So at every state you're in, there are as many arrows that go out as there are states, including the state itself. So there are 3 arrows that go out and 3 arrows that come in. And every arrow that goes out has a probability. Every arrow has a probability associated with it. This is A01, this is A02, and this is A00. And these 3 probabilities must sum to 1. Given that you are at some point, at some time t, in state S0, at then time t plus 1, you will be at one of the states. At all has to sum to 1. Okay? So this is called the transition matrix. This is the matrix that describes the dynamics of transitioning between parts of speech. And you can decide that some of these transitions are 0 because the grammar doesn't allow them. Fine, that's up to you. You can handcraft this matrix to be whatever you think it should be for the grammar of some language, or you can try to learn it from data. But if you're going to learn it from data, it looks like you will need to have somebody hand annotate the parts of speech of that data, right? In order to learn it straightforwardly from data. So that's a problem we'll get to in a minute. So this takes care of this part. In fact, I'm going to rewrite this joint likelihood as a product of A of Q I Q I plus 1. So the value of Qi is whatever state we were at times, I'll call it T now here, 2. Qt plus 1. So the first index of A is Qt, which means the state we are at time t. And the second index is the state we're at time t plus 1. No, it was conditioned here on -1. I have to be careful with the indices. Since we are conditioning this way, and we start with t equals 1, this is equals pi t goes from 1 to n, and this is A. The subsequence here is Qt minus 1, and then the second one is Qt. So the first one is from 0 to 1, the second from the state at time 0 to the state at times 1, the second one is state at time 1 to the state at time 2, and so forth. And then there's this part. What is this part? This is conditioned on knowing what the part of speech is at time t. What is the probability of a particular word that we see at position t? This is known as the emission probability. So HMMs have two kinds of probabilities, transition probabilities and emission probabilities. Why is it called emission? Because you're emitting an observable symbol. You're emitting something that people can observe. These are the transition probabilities. These are the emission probabilities. What would be the emission probabilities? Well, they're going to be some multinomials. Under the determiner, so P of a word, P emission of a word given the part of speech det determiner might be something like, how many determiners are there in English? Just 3, no? The, A, and N. Are there more?
Depends on how you define determiner.
Okay. So there might be more. But there will be some probabilities here. And all the other words might have 0. Or you might assign them a small probability. But basically it'll be a distribution over the words of your vocabulary that is specific to a part of speech. If you know it's a determiner, which word is it going to be? For nouns, it's going to be a much larger. If this is a singular noun here, then there's going to be a long list of all the words in English that could be singular nouns with some probability over them. And then all the other words that could not possibly be a singular noun might get 0, or you might be generous and give them a tiny probability or something like that. So the emission probabilities we will call B, and B will be a distribution over all the words in the vocabulary conditioned on the particular part of speech as J. Or we can call it B sub J, means it's conditioned on part of speech J, where J goes from 0 to big N, the number of parts of speech. Because the words come from a finite vocabulary, I can capture the BJs in a matrix too, although this matrix is going to be not necessarily rectangular. The transition matrix is rectangular, but this matrix is going to be, it goes from 0 to N here, but here, along the top, it goes from word 1 through word V. So it's of dimension N by V, or N plus 1 by V. And each row is going to be one of these. So this is going to be B1 of W, B2 of W, B0 of W, all the way to Bn, B sub N of W. And here you're going to have a whole, every row would be an entire unigram, right? A whole set of V values that sum to 1. Questions?
Just to clarify, Bi of W is the fact that B of W equal to Si, or
Bj,
You don't have to write SJ there.
yeah. Bj, B of W is B of W conditioned on the fact that the true part of speech was Sj. So J goes over indexes of or parts of speech. So I don't need to write both of these, but I can write either this one or that one. There are N plus 1, big N, N plus 1 parts of speech, and therefore there are N plus 1 unigrams, one for each part of speech. So this is a model that will assign every text a probability. Even if you're given the model, you're given the number of parts of speech, say N plus 1. You're given the transition matrix, big A, and you're given the emission matrix, which is big B. You've now been given everything there is to know about the model. So the HMM, the hidden Markov model, consists of the parameterization lambda, which consists of these two components, A and B. We just, A and B together we called lambda. This is like, captures all the parameters together. But really the parameters are the transition matrix, the emission matrix. Once you're given that, given the numerical value, you have the model in your hand, and you can, in principle, calculate the probability that this model assigns to any text. We did it here. So I should write here under knowing a particular model value. This is what determines the A's and the B's. Bj of W. Which W is that? WT. This is the probability that this model gives to this complete data, the word sequence and the hidden state sequence, if it were not hidden. Now, since it is hidden, somebody might ask me, how do I calculate given a model, given an HMM, namely lambda, which consists of an A and a B, and given text W1 through W small n is an index, is a number of tokens, calculate what is the probability of this word sequence under the model. I don't know how to do that right away because I don't know what the hidden state sequence is. But I can use my law of total probability to write this as a sum over all possible hidden state sequences. Remember that big Q means the entire sequence. It's like Q1 through Q big T. Oh, sorry, I called it big N. Let's call it big T here because the index here is small t. And now I can write the joint of W and Q. And this I know from here. Okay? So it is easy for me to write the likelihood of the joint, the complete data, both the visible and the invisible part. But if I want to write down the likelihood of the visible part only, I have to sum over all possible assignments of the latent part. Each one of these assignments I can calculate this way. How much computation is involved here? How many operations are involved in solving this for particular values of W and Q?
So you have to sum over the columns for a particular row to get Pj of word T?
No, I have this stored in memory. I have this matrix. Both matrices are stored in memory. I just looked them up.
So I think then it should take order n to compute the entire word.
Order n, to be more exact, it's 2n multiplications. I'm multiplying here, right? T goes from 1 to n, and by the way, I changed my mind and I call it big T now, right? Because the index has been changed to small t. So I multiply T of these and T of these. You can see it here. 1, 2, 3, 4, 5, T. And they're here. 1, 2, 3, 4, T. So they're, and I'm going to multiply, every one of the arrows has a term in the product. I'm going to multiply them all together. These are the transition terms. These are the emission terms. So this takes me 2T operations. That's completely doable, even if T is 100,000. That's no big deal, even if T is 1,000,000. But what if I want to calculate just P of W given the model, which is this? The probability of a given observable sequence, a given set of words, which is really what my model is eventually about. The hidden part is just my own hallucination, my own pretend. The real thing is what I see. To do that, I need to calculate this with 2T operations again and again for every possible sequence of hidden variables. How many sequences are there of hidden variables? How many different values of Q can there be?
T into S squared.
I don't know what into means.
T multiplied by
T multiplied by S. What is S? You mean the size of the set S, the number of parts of speech? That would be N, big N, or N plus 1. It'll be exponential. So it will be N possible parts of speech for the first word, times N possible parts of speech for the second word, times N possible parts of speech for the third word, right? All the way to the Tth world. So that would be N to the power of T. I also pretended that there are N plus 1 parts of speech. So it'll be N plus 1 to the power of T. Okay, close enough. So to calculate this, I need N to the power of T steps, and in each step I have to multiply it by 2T. But that's small change. This is the killer. T can be very large. So even if N is 3, even if N is 2, this is still exponential. So I have a problem to calculate the likelihood of any observed sequence based on an HMM, even a simple first order HMM. It appears that I need an exponential amount of computation. I say it appears because it's not true. I can actually calculate it exactly, not an approximation, in polynomial time, but not the method I showed you. So I can use another method using the idea of dynamic programming, which I will do when we meet again, to calculate the likelihood of data in polynomial time. What I want you to take home from this is A, whenever we deal with latent events that themselves have a Markovian relationship as they evolve, that's an HMM. A mixture of Gaussian you can think of as a special case of HMM, but the HMM is of degree 0, of order 0, so there's really no relationship. Every time you come to generate a number, you don't rely on what happened in the past. You don't care what the last Gaussian was. You generate a new Gaussian. That simplifies things. But it's a special case. In a more general case, the next latent event is not drawn independently. It's drawn conditioned on what the last one was. So that's the first message. That's an HMM. The second message is HMMs are fully specified by two sets of probabilities. The transition probabilities that govern the progression, the first order Markov progression of the latent variables, namely the part of speech, and the emission probabilities, which are the conditional probabilities of what you observe conditioned on what latent state you're in. Specifying both of these matrices fully specifies the model. That's the second point. The third point is that calculating something as simple as the probability of some observable sequence given the model is not that straightforward. On the surface, on the face of it, it looks like it requires exponential amount of computation.